Okay, so welcome to section 11.4, which is on series. Okay, so definition. What is a series? So a series is a sum of what? Of a sequence. A sequence let's say, how do I want to say it? A sub n So number one, a finite series sums the first n terms. Number two, an infinite series. An infinite series oh boy. An infinite series sums all terms. So we're assuming the sequence is infinite here. So the notation will be why is this not autocorrecting? Come on. So number one. So the first notation will be the sum sigma, as my index I counts from 1 to n of a sub index. So this is equivalent to a1 plus a2. Notice it's a sum plus a3 plus dot 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 plus a sub n, where it's finite. So I'm adding the first n terms of the sequence. My index, actually I will define those in a moment. So number two is an infinite series. So that's going to be the sum as index counts from 1 and goes on to the infinity of a sub index. So that's going to be a sub 1, because I start counting at 1, a sub 2, a sub 3, plus dot dot dot. I go on forever. So that one never ends. So these are the two types of sums. And terminology. So we have sigma, we have index, I'll say 1, 2, what color should I use on top? Let's do orange. Of a sub-index. Okay, so the terminology is going to be sigma is read aloud. So this is, the way I read it is the sum sigma. So you'll hear me say the sum sigma as index. So I is index. As the index I counts from 1. So this is the lower limit from where we start. To n, which is the upper limit. And then I'll say of the sequence a sub index. The sequence a sub I. So the way I would state this aloud is given by, what color should I use? So quotations. The sum sigma used all those colors. Well, I'm going to use a darker orange. So as index I counts from 1 to n, maybe I should have made these a bit lighter because they kind of look like orange, which they're not. So let me make them a bit lighter. Okay, that looks a bit better. So as index I counts from 1 to n of the sequence, so of the sequence A sub I. So that's how I would state that symbol aloud in words. Okay, so definition. So when did I? Yeah, so the nth partial sum, that's what we're defining now. So the nth partial sum of a series is given by S sub n is going to be the sum sigma as my index counts from 1 to n of A sub index. Okay, so basically an nth partial sum stops taking the sum at n. Okay, so for example, so find the nth partial sum. Find S sub n for the following infinite series. And they could be finite series, it doesn't matter. But I'm just going to give them as infinite. So let's say we have the sum sigma as my index I counts from 1 to the infinite of 1 over index. And I want you to find the fifth partial sum. So we want the sum of the first 5 terms. So I claim that that's going to be 1 over 1, because my index starts counting at 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, and finally plus 1 over 5. So notice I've just plugged in index into the denominator here and counted from 1 all the way up to 5. So what do we have here? The common denominator is going to be, of course, well, 5 times 4 times 3 times 2 times 1. I believe that's 5 factorial. So what is missing? 5 factorial divided by 1 is 5 factorial. So the first term is 5 factorial. Plus the second term is 5 factorial divided by 2. Well, what is 5 factorial? Off to the side. 5 factorial is going to be 5 times 4 times 3 times 2 times 1, or vice versa. So 3 times 2 is 6. 6 times 4 is 24. And 5 times 24 is 120. Okay, so what is 120 divided by 2? Well, I claim that that's 60. And in fact, let me go ahead and just rewrite the first term as 120. Okay, what is 120 divided by 3? Well, I claim that that's 40. So that's the third term. What is 120 divided by 4? Well, I claim that that's 30. And what is 120 divided by 5? Well, I claim that that's 24. So what do we have here? We have 120 plus 60 plus 40. That's 100, so that's 220. Plus 30 is 250. So I claim we have 274 divided by 120. Well, each of those is even. So let's see if I can at least reduce a 2. So this will be 2 times 137 divided by 2 times 60. So that reduces then. The 2's reduce. Notice I'm not crossing out the 2's, I'm checking them out. Okay, 137 divided by 60, and I think that'll do. So that is the sum of the first 5 terms. That is the 5th partial sum of that series. Okay, so number 2. Let's say we have the sum sigma as my index counts from 1 to the infinite of 1 over index factorial, and I want to find the third partial sum. Okay, so I claim that the third partial sum is going to sum as my index starts counting at 1. So that's 1 factorial. And then goes on to 2. That's 2 factorial. And then goes on to 3, and that's where I want my sum to stop, 3 factorial. Okay, so this is going to be common denominator, I claim is 3 factorial. 3 factorial. Okay, so let's note off to the side. 3 factorial is 3 times 2 times 1, which is just 6. Okay, so 3 factorial divided by 1 factorial. Well, let's also note 2 factorial is 2 times 1, which is 2, and 1 factorial is 1. Let me write that a bit better. 1 factorial is 1. That's even worse. Okay, so what is 6 divided by 1? That's going to be 6. What is 6 divided by 2? That's going to be 3. And what is 6 divided by 6? That's going to be 1. So I claim that those are the numerators. Okay, so let's go ahead and see what we have here. 6 plus 3 plus 1 is 10. Divided by 3 factorial, we know is 6. Each of those is divisible by 2. So 2 goes into 10 5 times, and 2 goes into 6 3 times. There we are. So the third partial sum of that series is 5/3. Third time's a charm. Okay, so let's say we have the sum sigma as my index counts from 1 to the infinite of 2 to the index. And let's say I want to do the 5th. Should I do 5th? Let's do 4th. I've already done 5th partial sum. Okay, so we have this 4th partial sum. Do I have ants on me? Probably. So the 4th partial sum will be 2 to the 1st, because my index starts counting at 1, plus 2 to the 2nd, so 1, 2, plus 2 to the 3rd. Remember, it's a sum. There's pluses in between. Plus 2 to the 4th, and I can stop there. So this is 2 plus 4 plus 8 plus 16. Okay, 2 plus 4 is 6, plus 8 is 14, plus 16 is 30. Hopefully I did that right. Right? Did I? 16, 8, 24, 28, 30. Yeah, okay. Okay, so let's consider something that my instructors always told me any 6-year-old child could figure this out. And the reason they said that is because a 6-year-old child did figure it out. So let's consider the sum sigma as my index starts counting at 1 and stops counting at 100 of just index. So this is going to be the 100th partial sum. So I claim that the 100th partial sum is going to be equal to, in this case, for that particular series, I start counting at 1, 2, 3, 98, 99, 100. But I also claim that the nth partial sum, S100, can be written as 100 plus 99 plus 98 plus dot 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 plus 3 plus 2 plus 1, right? I can count backwards. Doesn't matter. Still the same sum. Okay, so what I'd like to do is I'd like to add these two together. So on the left-hand side, I'll have 2 of the 100th partial sum. But now, in fact, you know what? Maybe I should have left a line in between. I'm going to leave a line in between so you see what I'm doing here. So what I'm going to do, I'm going to add 1 and 100. When I do that, I get 101. Then I'm going to add 2 and 99. When I do that, I get 101. Then I'm going to add 3 and 98. When I do that, I get 101. Then I'm going to add 98 and 3. When I do that, I get 101. Oops, wrong color. Sorry. Ugh. 101. Then I'm going to add 99 plus 2, which is also 101. Then finally, I'm going to add 100 plus 1, which is 101. So how many times have I added 101 to himself? If I started counting at 1 and stopped counting at 100, this is 100 times. Okay, so I have that 2 times the 100th partial sum will be 100 what's? 100 101s. So now I can divide both sides by 2. And I get the sum of the first 100 integers is 100 over 2 times 101, which I claim is 50 times 101, or 50/50. So that is the sum of the integers from 1 through 100. And Euler discovered that when he was a 6-year-old child. So hence why my instructors would say any 6-year-old child could do that. If you're a famous mathematician. Okay, so theorem. So the nth partial sum of an arithmetic series is given by S sub n will be n divided by 2 times the quantity a1 plus a sub n, where, since it's arithmetic, a sub I is going to be a1 plus I minus 1 times the common difference d. Right? Remember that? For an arithmetic series. So let's prove this. So proof. Okay, so let's recall. We have that, let me use a lighter. A sub n was a1 plus n minus 1 times d for an arithmetic sequence. What am I saying? So that means that a sub n minus 1 a sub n minus 1 is just a1 plus n minus 2 times d. So that's a1 plus n minus 1 times d minus d. But of course, these first two terms here are a sub n. So we get that a sub n minus 1 is just a sub n minus d. Okay? And that makes sense, because if you're adding d to get to each next term, then the previous term, you subtract d. Okay, so I claim that S sub n, the nth partial sum of an arithmetic series, will be, well, a1 plus a2 plus dot 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 plus a sub n minus 1 plus a sub n. So that's really a1 plus the common difference d, right? And a1 plus twice the common difference d, because n minus 1 is 0 in the first, 1 in the second, 2 in the third, etc. Then we have, counting backwards from the top, this will be a sub n minus twice d. Then a sub n minus d for a sub n minus 1, and then just a sub n. Okay, but I can do this a different way, right? I can go backwards, and let me skip a line. So S sub n can also be thought of as a sub n plus a sub n minus d plus a sub n minus 2d plus dot dot dot. Now going forwards, this can be thought of as a1 plus 2d. This can be thought of as a1 plus 1d. And finally, a sub 1. So what I'd like to do is I'd like to add these two together. So I claim that I'll have 2 times the nth partial sum will be, well, if I add these two, I will have a1 plus a sub n. If I add these two, notice that the d's sum to 0. So I'll have a1 plus a sub n plus dot dot dot. Notice that again, I would have a1 plus a sub n. And similarly, here and here. So I'm going to get here, I will have once again a1 plus a sub n plus a1 plus a sub n. And finally, plus a1 plus a sub n. Okay. So how many terms have I done this for? Do you know what? Maybe I'm going to erase. I don't have enough room, so I'm just going to move these guys over a bit. And skip the two middle terms because I don't have enough room. Okay, so do you agree that the nth partial sum has n terms? So this will be n times. So I claim that twice the nth partial sum is going to be n times a1 plus a sub n, because I'm adding it to himself n times. So now I'm just going to divide both sides by 2. And I get that the nth partial sum is going to be n divided by 2 times the quantity first term plus the nth term. And that's exactly what the theorem says, right? So check mark, we've proven it. So check mark, proof is complete. Okay, so given that, let's evaluate the following. So example, evaluate the following. Okay, so number 1, let's say we have the sum sigma as index I counts from 1 to 50 of, let's do 2 plus 3i. Okay, so we have the sum as index counts from 1 to 50 of 2 plus 3 times the index I. Okay, so I claim that A1 is going to be 2 plus 3 times 1, which is 5. I claim that A sub n, so what should I do there? Let's do green. A sub n, which in this case is 50, is going to be 2 plus 3 times 50, which is going to be 153. I claim that n itself is 50. Okay, do I have enough to plug into the formula? Yeah, I do. So I claim that the 50th partial sum here is going to be n divided by 2 times the quantity 5 plus 153. Is that true? Is that n divided by 2 times first term plus last term? Yeah, hopefully it is. So what's 50 divided by 2? That's 25 times what amounts to 158. Okay, so how would I figure out what is 25 times 158? Well, since I don't have a calculator, I'm going to have to figure out this way. So I do 1, 5, 8, and then, 25, and I have this grid here. Okay, so what is 1 times 2? It's 2, so 0, 2. What is 5 times 2? It's 10, so 1, 0. What is 8 times 2? It's 16, so 1, 6. What is 5 times 1? It's 5, so 0, 5. What is 5 times 5? It's 25. What is 8 times 5? It's 40. Okay, so I'm going to go ahead and put my diagonals. Now, usually I would do this very quickly off to the side on my paper. It really doesn't take very long. So what do we get when all is said and done? Summing the rightmost diagonal, we get 0. Then 6, 4, and 5 is 15, so I carry the 1. 5, 6, 7, 8, 9. Then 3 and 0. So I claim that the sum, the 50th partial sum, let me move this up, is going to be 3950. Okay. Let's do another one. Do we have enough room? Yeah, I'll just go to the next page. So number 2, I think. Is that number 2? Yeah. So let's say we have the sum sigma as my index counts from 1 to 100. Let's do 4 minus I. Okay, so let's rewrite this. Did I rewrite it? Yeah, I did. So we have the sum sigma as my index counts from 1 to 100. Do I have the wrong colors? Yeah, oh well. Of the quantity 4 minus the index. Okay, so what is a sub 1, the first term? A sub 1 is going to be 4 minus 1, which is 3. Let me use, boy, I want to use a different color, but there is no good colors, are there? I've already used orange. Use a darker orange. A sub n, which is 100 in this case, is going to be 4 minus 100. So of course that's going to be negative 96. N, we know, is 100. Okay, so all together, I claim that the sum, the 100th partial sum, is going to be n, which is 100, over 2, over 2 times the quantity, a1, which is 3, plus a sub n, which is a sub 100 in our case, which is negative 96. So I have that the 100th partial sum for that series is going to be 100 over 2 is 50, and 3 minus 96 is negative 93. Okay, so once again, let's go ahead and figure this out. We'll have 93 times 50. Okay, guess it wanted to make a perfect square, but why is it not working for me? Of course it's not going to work. Okay, so I will just do it line by line. Oh, well, that's why, because I didn't do these right. Let me move this over. And is that better? Maybe, I guess that's better. Okay. This looks so small. Okay, so what do we have? 9 times 5 is 45. 5 times 3 is 15. And 0 times anything is 0. My favorite numbers. Okay, so let's go ahead and calculate this. So starting from the rightmost, you have 0, 5, 6, and 4. So I claim that the 100th partial sum of the series in this particular question is going to be 4650. Okay. Okay, did I do that right? I hope I did. Anyways, yeah. Okay, number 3. Let's say we have, let's do the sum sigma as my index counts from 1 to 99 of 6 plus twice the index. Okay. So we'll have the sum sigma as my index counts from 1 to 99 of 6 plus twice the index. Okay, so I claim that a sub 1, the first term of this, will be 6 plus 2 times 1, otherwise known as 8. I claim that a sub 2, sorry, why do I keep on saying 2? A sub 99, the nth term here, is going to be 6 plus 2 times 99. So 2 times 99 is 198, plus 6 is going to be 204. And of course, n is 99. So the 99th partial sum, s sub 99, is going to be n, which is 99, divided by 2, times the quantity, first term, 8, plus the last term, 99. So the 99th partial sum is going to be 99 over 2. Well, that's a terrible number, isn't it? 99 over 2, that's not going to work out nicely, times 8 plus 99 is 107. So what I'm going to do off to the side is I'm going to say, okay, what is 107 times 99? And then I'll divide that answer by 2 once I'm done. Yeah, I really messed that up, didn't I? Okay, so 1 times 9 is 0, 9. 0 times anything is 0. 7 times 9 is 63. So 63, 0, 0, 0, 9. Okay. So what do we have here? So from right to left, we have 3, 9, 15, carry the 1, and 10, carry the 1, 1. Okay, so the 99th partial sum is going to be 10, 5, 9, 3 divided by 2, whatever that is. I'll just leave it like that. Okay, so hopefully that's making sense, and these are pretty miserable. So let's move on to something that's actually much nicer, even though it involves more, a quote, more difficult series. So theorem. Okay, so the nth partial sum of a geometric series, meaning each of the terms are a geometric sequence, is given by so the nth partial sum is going to be a times 1 minus r to the n divided by 1 minus r, where a is the first term, r is the common ratio, okay, so provided, what's a caveat? Provided r is not equal to 1, right? Thou shalt not divide by 0. So let me make sure I put that very important. R not equal to 1, thou shalt not divide by 0. Okay, so let's prove this. Proof. Okay, so the nth partial sum of a geometric series. Well, what is a geometric sequence? It's ar to the n minus 1, right? So it's going to be a plus a times r plus dot 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 plus ar to the n minus second plus AR to the n minus first, right? It's always to the n minus first. Okay, now let's consider R times S sub n in the same order. So that's going to be AR. Shoot, probably shouldn't have done that, should I have? So that's going to be AR plus AR squared plus AR to the n minus first plus AR to the n, because now I have one more power on R. And what I'd like to do is I'd like to subtract instead of adding this time. So let's subtract. So what I'm going to have is S sub n minus R times S sub n on the left, the nth partial sum. And what that's going to be is if I subtract, the first term is going to be A minus AR. Then I'm going to add to that, actually let me show where the subtraction is. It's inside. Then I'm going to add the next subtraction, which will be AR minus AR squared. Then I'm going to add AR to the n minus second minus AR to the n minus first plus, oh shoot, I don't have a lot of room. Let me move this to the left. Need just a little bit more room. Then I'm going to have AR to the n minus first minus AR to the n. Okay. Still don't have enough room. Let me move this just a bit more. Guess it doesn't really matter, but it's driving me crazy. Okay. Do you agree that negative AR and positive AR go away? And if n were 4, this would be AR squared right there. So those middle guys go away. And then AR to the n minus 1 negative and AR to the n minus 1 positive also go away. So what I'm left with, if I factor out S sub n, I'll have 1 minus R, and that'll be equal to just simply A minus AR to the n on the right. So I have that S sub n times the quantity. Actually, let me just copy it. 1 minus R is going to be equal to, let's factor out the A on the right. And when I factor out the A, what's left is 1 minus R to the n. So let's go ahead now and divide both sides by 1 minus R. And I get that S sub n is equal to A times the quantity 1 minus R to the n divided by 1 minus R, check mark, because that's what we claimed it was right here. Okay, so we've proven it. Do you know what, let me move this a bit over to over here. I will use a dashed arrow to show that. Okay. So, for example, let's use this theorem now. Okay, so find the nth partial sum for the following. A geometric series. So number 1, let's say we have the sum sigma. As my index starts counting at 1, goes on forever, of 2/3 to the index minus 1. And let's say we want to find the fourth partial sum. Okay, so the fourth partial sum, we'll start counting at 4 minus 1. Oh, sorry, what am I saying? 1 minus 1. Okay, what is wrong with me? 1 minus 1 plus 2/3 to the 2 minus 1 plus 2/3 to the 3 minus 1 plus 2/3 to the, finally, 4 minus 1. So this is the fourth partial sum because my index has arrived at 4. So what do we have here? We have 2/3 to the 0 power plus 2/3 to the first power plus 2/3 squared plus 2/3 cubed. Okay, so that gives us 1 plus 2/3 plus 4/9 plus, where am I? Squared is 4, 2 cubed is 8, 27ths. So the lowest common denominator here is 27. 1 into 27 is 27. 3 into 27 is 9, so 2 times 9. 9 into 27 is 3, so 4 times 3. And 27 into 27 is just 1. So what do we have here? We have 27 plus 18 plus 12 plus 8 all over 27. Well, 12 plus 8 is 20, right? 20 and 27 is 47. If I added another 20, it would be 67, but I'm too shy, so I claim it's 65 over 27. Not pretty, but there it is. Okay, so let's do number 2. Let's go down to the next page. Let's say we have the sum sigma as my index counts from 1 to the infinite of 5 times 1/4 to the index minus 1. Oh, what am I doing? Do you know what have I done? I've done it the hard way, haven't I? All of this, wow, okay. Yeah, I forgot I was doing it the easy way. So, oh my goodness. S sub, what was this, 4? It should be A, which is the first term, times 1 minus R, the common ratio, to the n, rather, to the fourth, over 1 minus the common ratio. Okay, so I forgot to do it that way. Must be 2 in the morning. Okay, so what is A? What is attached here in front? Just a 1. So I claim that this is 1 times the quantity 1 minus the common ratio here is 2/3. And we're raising that to the fourth power and dividing that by 1 minus 2/3. So I guess that's a good check to do it the long way first. Okay, so I claim the numerator will be 1 minus 2 to the fourth is 16. 3 to the fourth is, what is 3 to the fourth? That's going to be 81, right? All over 3/3 minus 2/3 is 1/3. So 81 minus 16 is going to be what? Well, that's the same as 80 minus 15, right? So 80 minus 15, oh, look at that, that's 65 over 81, which we're dividing by 1/3. And dividing by 1/3 is the same as multiplying by 3, right? So 3 goes into 81 how many times? 27, right? So 3 goes into 81 27 times. And look at that. It's the same, so much easier. Why did I do all that work? Because I wasn't paying attention. So let me pay attention now, shall I? Make our lives much easier. Let's do S sub 3. Okay. So I claim that S sub 3 is going to be, now the easy way is going to be A times the quantity 1 minus common ratio to the n, in this case 3, divided by 1 minus the common ratio r. Okay, so now we have a different A. The common ratio A is what's attached, the 5 here. This will be 1 minus the common ratio is 1/4. To the n is 3. We're going to divide this by 1 minus 1/4. Okay, so this is going to be 5 times the quantity 1 minus 1/64 divided by 4/4 minus 1/4 is 3/4. Okay, so what do we have? That's going to be 5 times 64 minus 1 is 63 over 64, so this is going to be 63 over 64 times the reciprocal of what's in the denominator, 4 over 3. Okay, so 4 goes into 64 16 times, and 3 goes into 63 21 times. So what do I have? I have 5 times 21, which is 105 in the numerator. Then I have 3 times 16, which is 48 in the denominator. So there we are. Okay, so number 3. Let's say we have the sum. Sigma as index counts from 1 to the infinite of negative 3 times 1/2 to the index minus 1. And let's say we want the fifth partial sum. Okay, so I claim that the fifth partial sum is going to be A times 1 minus the common ratio r, in this case to the fifth, divided by 1 minus the common ratio r. Okay, so in our case, A is negative 3. This is going to be 1 minus the quantity 1/2 to the fifth, all divided by, come on, autocorrect, 1 minus 1/2. So that's going to be negative 3. And we're going to have 1 minus 2 to the fifth is 32, so this is 1/32 all over. 1 minus 1/2 is just 1/2. So I will have negative 3 times 32 minus 1 is 31 over 32 times the reciprocal 2 over 1. Okay, so 2 goes into 32 16 times. So what I'm going to get is negative 3 times 31 is negative 93 divided by 16. And there we are. That is the sum. Okay, so let's note something about fractions and powers. So note. Do you agree that 1/10, comma, 1 100th, comma, 1 1,000th, comma, 1 10,000th, etc. can be written as 1/10 to the first power, comma, 1/10 to the second power, comma, because the power tells me how many zeros I tack on, etc. Actually, I wrote one more term. So let me write one more term here. 1/10 to the fourth power, etc. So what's happening as my denominator, or as my fraction, is raised to a higher and higher power? So as n approaches the infinite, 1/10 to the n gets closer to 0, approaches 0. So that is, i.e. id est, i.e. the limit as n becomes infinite of 1/10 to the n is 0, right? Remember that notation from the first 8 weeks of our course? Okay, or trigonometry rather. Okay, so theorem. Okay, so for the absolute value of r being strictly less than 1, that is r between -1 and 1, non-inclusive, this implies that the limit as n becomes infinite of r to the n is 0. So as n gets larger and larger, r to the n gets smaller and smaller. Okay. Well, let's consider something. So let's consider the limit as n becomes larger and larger of a times the quantity 1 minus r to the n over 1 minus r for the absolute value of r being strictly less than 1. Well, this is going to be equal to let me just write it here. This is just going to be equal to a times 1 minus 0 over 1 minus r, because the limit as n becomes infinite of r to the n is 0. So this term goes to 0, right? So what is that? That's just a times 1. So that's just a. I'm really having trouble writing at this time of night. I need my full moon to give me back all my powers. Okay, so a over 1 minus r, right? So hopefully that's making sense, because that r to the n was small. It went to 0 as n got bigger and bigger. So this leads us to a theorem. So if n is infinite, so theorem. So the sum of an entire infinite geometric series is given by the sum, sigma, as my index counts from 1 to the infinite, of ar to the index minus 1, is going to be a over 1 minus r. Okay, provided the absolute value of r is strictly less than 1. Okay, so for example, evaluate the following. So number 1, let's say we have the sum, sigma, as my index counts from 1 to the infinite, of 2 times 1/3 to the index minus 1. Okay, so we have the sum as my index counts from 1 to the infinite of 2 times 1/3 to the index minus 1. Well, I claim that that's going to be a over 1 minus r. That's it. So this is 2 over 3/3 minus 1/3 is 2/3. So the 2's reduce, so I invert and multiply, and I get 3. So this is amazing. This is an infinite sum. This goes on forever. And yet I can get a finite value for something that keeps on adding and adding and adding. Where should I put this? Maybe I'll put it here. So I think this is amazing that you can add something forever. You're still adding something, and yet you get a finite value, only 3, with infinitely many terms. That's incredible. Okay, what about 0.3 bar? Speaking of 3's, well, I thought we were doing infinite series, infinite geometric series. Well, we are. I'm just being sneaky. Because 0.3 bar is actually 0.3333, etc. And that's really 0.3 plus 0.03 plus 0.003 plus 0.0003 plus ... Forever and ever. Amen. Agreed? I'm just taking each place and writing it as its own term. Okay, well, there's 1 0 preceding that, so it's 3 over 10. Now there's 2 zeros preceding it, so it's 3 over 100. Now there's 3 zeros preceding it, so it's 3 over 1,000, etc. 10,000. Okay, so what I'm going to do is I'm going to factor out the first term, 3/10. And in fact, I'm going to factor it out in purple for a very specific reason. So when I factor out 3/10, I get 1 plus 1/10 plus 1 100th plus 1 1,000th plus ... Forever and ever. Amen. So this gives me 3/10 times the quantity. Well, I claim that 1 can be written as 1/10 to the 0, and that 1/10 is 1/10 to the first, and 1 100th is 1/10 to the second, and 1 1,000th is 1/10 to the third. So notice I started my exponent at 0. So I claim that this is going to be the sum sigma, as my index counts from 1 to the infinite. Every term I'm going to distribute that 3/10 to. But this will be 1/10. Well, my first term is 0, so I claim it's index minus 1, because I start with 0. Okay, well, that sum I know to be A, 3/10 divided by 1 minus R, 1/10. Okay, so that's going to be 3/10 divided by 9/10. So invert and multiply, and you get 3 over 9, or 1/3. So, well, it's true. 0.3 bar is 1/3. We did all that for something we already knew. Oh, yes, mathematicians are evil. Let's do another one, shall we? So 1, 2, 3. And I guess I'll let this one be the last one. So let's say we have 2.27 bar. Okay, so once again, 2.27 bar is 2.27272727, etc., forever and ever. So I claim that this is 2 plus 0.27 plus 0.0027 plus 0.00027 plus ... Okay. Well, I claim that that'll be 2 plus 27 divided by 100 plus 27 divided by, add 2 more zeros to 100 because I'm moving 2 more places, plus 27 divided by 1, 2, 3, 4, 5, 6, 2 more zeros, etc. So I claim that this is 2 plus, I'm going to factor out a 27 over 100 from all terms not equal to 2. So I get 1 plus 1 over 100 plus 1 over 10,000, etc. So this is 2 plus 27 over 100 times, well, I think the common ratio is 1 over 100 to the 0 plus 1 over 100 to the first plus 1 over 100 to the second. So I claim that this is 2 plus the sum sigma, as my index counts from 1 to the infinite, of 27 over 100 times the common ratio 1 over 100, and the exponent starts at 0, so it's index minus 1. So that's a geometric series. So I claim that this is 2 plus a, 27 over 100, divided by 1 minus r, 1 over 100. So this will be 2 plus 27 over 100 times the reciprocal of 99 over 100, so 100 over 99. So I claim that this is 2 plus 27 99ths, each of which is divisible by 3. So this is 2 plus, well, actually they're both divisible by 9, so I claim this is 3 over 11ths. Okay, so 22 plus 3 is 25 11ths. So notice we get something finite from something infinite, seemingly infinite. So this series sums forever and ever, but we know that 11 goes into 25 about 2 and 0.27 times, approximately. Okay, anyways, this is the second to last section. The next one is not in the book, and I'll see you there.